Hey everyone, welcome back to channel Code with AKJ. Today is day 19 of solving LeetCode Scientific Challenge, and today's problem is find pivot index. So the problem statement says, given an array of integers num, calculate the pivot index of this array. The pivot index is the index where the sum of all the numbers strictly to the left of the index is equal to the sum of all the numbers strictly to the index right. So if the index is on the left edge of the array, then the left sum is 0 because there are no elements to the left. So this also applies to the right edge of the array. And finally return the leftmost pivot index, and if no such index exists, return -1. So today we'll tackle a classic problem, find pivot index. So we'll start with our brute force approach and we'll optimize it to achieve better efficiency. So let's dive in. So the problem statement is simple. So given an array of integers, you need to find the pivot index. And here the pivot index is where the sum of all the elements of the left is equals to the sum of all the elements on its right. And if no such index exists, we'll return -1. For example, given array nums here 1, 7, 3, 6, 5, 6. Here the pivot index is 3 because at this particular index the left sum, that is nums of 0, 1, 2, gives us level, and nums of 4, 5, which is on the right side of this given index 3, is 5 plus 6, which gives us level. So here the left sum is equals to right sum. So at this particular index, this particular condition holds, so we return this particular index as our pivot index. And coming to our example 2, we have three elements, that is 1, 2 and 3 in this given nums array, and there is no index that satisfies this condition where the left sum is equals to right sum, so we'll return -1 in this case. And same goes with our example 3. Here in this case the pivot index is 0, which is the first element itself. The left sum of this first index would be 0 and the right sum of this particular index would be 0, that is 1 plus -1. So in this example we'll return index 0. So let's start with our brute force approach. The idea is simple here. So for each index we'll calculate the sum of elements to the left and to the right, and we'll compare the two sums. If they are equal, that's our pivot index, and if no such index is found, we'll return -1. That is, for every index I, so first suppose we'll start with index 0. So for this particular index I, we'll calculate the left sum and the right sum, and we'll compare these two sums, left and right, and if they are equal, we'll return this particular index I, and if not, we'll return -1. So for this particular index I, if both sums are not equal, we'll move on to our next index. So for this index, we'll calculate again the left sum and the right sum, and we'll compare this new left sum and right sum. So if they are not equal, we'll again move to our next index, and in this way we'll check for every index I its left sum and right sum. So this would be our brute force approach. So since we calculate the left sum and right sum for every index I, the time complexity of this approach will be O of n square, and space complexity of this approach would be O of 1. So let's move on to our code and let's submit. So here's the code for our brute force approach. I have iterated over this nums array. I have calculated the left sum and right sum for every index I using these two for loops. One for loop is for the left sum and another for loop is for the right sum. And after calculating the left sum and right sum for this particular index I have compared these two sums, and if they are equal, then we'll return I, or else we'll move for next index I. So after finishing our whole for loop, if we have not found such pivot index, we'll return -1 at the end of our code. So let's quickly run this code. It's getting accepted, so let's submit. As you can see, it gets accepted successfully, but here the time complexity would be O of n square, which is not efficient for larger arrays. So let's quickly optimize this approach and bring down our time complexity. So now let's optimize this using the concept of a total sum. So the steps of our optimal approach would be to compute the total sum of this array and store it in a variable ts. We'll use a variable left sum as well, which will help us to track the sum of elements to the left of this current index I. And for each index, the right sum can be derived as total sum minus left sum minus the current value. So this would be our right sum. So in this way, we'll check for every index I if left sum is equals to right sum in a single loop. So since the total sum here is computed in O of n time complexity and a single loop to check the pivot index, the total time complexity for this approach would be O of n and the space complexity here would be O of 1. So as you can see, the time complexity is been optimized from O of n square to O of n, which is highly efficient for larger arrays as well. So let's quickly move on to our code and let's do a dry run for this given example. And finally, we'll analyze the time complexity and space complexity of both the approaches we have discussed. So here's the code for our optimal approach where we have used total sum concept. So we have taken two variables, total sum and left sum. We have calculated the total sum, which is the sum of the elements in our nums array, and finally iterated over this nums array to check if the left sum is equals to right sum. So if these two left sum and right sum becomes equal, we'll return that index I. And after finishing our for loop, if we haven't found any such index, we'll return -1 at the end of our code. So let's quickly run this code. It's working, so let's submit. As you can see, this code gets accepted successfully. Here the time complexity is highly efficient when we try to compare with the brute force approach time complexity. So let's quickly dry run our optimal approach using this given example 1, and let's finally analyze the time complexity and space complexity of both the approaches. So let's quickly dry run using this given example. So the total sum of this given array would be 28. So let's start with our index 0. So here the left sum would be 0 and right sum would be 28 minus left sum 0 minus the current value 1, which is 27. So since they are not equal, we'll move to our next index. So here for this given index value, the left sum would be 1 and the right sum value would be 28 minus 1 minus 7. That is 28 minus 8, 20. So since they are not equal, we'll move to our next index. Here the left sum would be 8 and the right sum would be 28 minus 8 minus the current value 3, which is 17. So here since they are not equal, we'll move to our next index. Here the left sum would be 11 and the right sum would be 28 minus 11 minus the current value 6. So here the value would be 11. So in this case, the left sum value is equals to right sum value. So the condition satisfies, and here in this given example, we'll return this particular index, which is index 3. So the answer for this example would be 3. So this was a pretty quick dry run of this given example using our optimal approach where we have used total sum concept and we have calculated our pivot index in O of n time complexity and O of 1 space complexity. So let's analyze the time complexity and space complexity of both the approaches. So the brute force approach takes O of n square time complexity as we are trying to calculate the left sum and right sum for each and every index I, and space complexity was O of 1. Whereas in our optimal approach where we have used total sum concept, the time complexity was O of n and space complexity was O of 1. So the optimal approach is highly efficient for larger arrays as well. So that's all for today. We have explored the pivot index problem starting with a brute force approach and optimizing it in O of n. So if you found this video helpful, don't forget to like, share and subscribe. Hit the bell icon so you never miss an update. I'll see you in the next video. Thank you.